CAN bus explained. A simple intro. Struggling to find an intro to CAN bus written in layman's terms? So were we. Therefore, we decided to launch a series of simple CAN intro articles written by one of our non-engineers to make sure it stays simple. Enjoy. What's CAN bus all about? Imagine that your car is like a human body. The controller area network system, CAN bus, is the nervous system, facilitating communication between all parts of the body. Similarly, nodes, or electronic control units, ECU, are connected via the CAN bus, which acts as a central networking system. In an automotive CAN bus system, ECUs can, in example, be the engine control unit, airbags, or the audio system. A modern car can have up to 70 ECUs. This is where the CAN standard comes in handy, as it allows ECUs to communicate with each other without complex, dedicated wiring in between. In turn, this allows for several features to be added via software alone, an example, electronic gearbox control. Indeed, that is the primary purpose of CAN, to allow any ECU to communicate with the entire system without causing an overload to the controller computer. But why is CAN so popular? 5 key reasons. 1. Low cost. ECUs communicate via a single CAN interface. In other words, not analog signal lines, reducing errors, weight, cost. 2. Centralized. The CAN bus system allows for central error diagnosis and configuration across all ECUs. 3. Robust. The system is robust towards failure of subsystems and electromagnetic interference, making it ideal for, an example, vehicles. 4. Efficient. CAN messages are prioritized based on IDs so that the highest priority IDs are non-interrupted. Critical, an example, vehicles. 5. Flexible. Each ECU contains a chip, allowing it to receive all transmitted messages, decide relevance, and act accordingly. This allows easy modification and inclusion of additional nodes such as CAN bus data loggers. The CAN bus history in short. Pre-CAN car ECUs relied on increasingly complex point-to-point wiring. 1986, Bosch developed the CAN protocol as a solution, releasing it at a SAE Congress. 1991, Bosch published CAN 2.0 Inclusion, CAN 2.0A 11-bit, and CAN 2.0B 29-bit. 1993, CAN is adopted as international standard, ISO 1189-8. 2012, Bosch released the CAN FD 1.0, aka CAN with flexible data rate. Today, almost every new European car comes with a CAN bus system, and it is used broadly in trucks, buses, industry vehicles, ships, planes, and industrial automation. Further, more exotic cases include drones, radar systems, submarines, or even prosthetic limbs. Looking ahead, the CAN bus system will stay relevant, and most likely even more so with the rise of, example, cloud computing, Internet of Things, IoT, and autonomous vehicles. What does a CAN message look like? To understand how the CAN bus system works, let's break down the messages sent over the network. The 11-bit identifier, CAN 2.0A messages, look similar, but with shorter CAN IDs. The 8 key parts of a CAN message are as follows. SOF. The start of frame is a dominant 0 to tell the other ECUs that a message is coming. CAN ID contains the message priority, as well as functional address, an example, RPM, wheel speed. RTR, the remote transmission request, allows ECUs to request messages from other ECUs. Control informs the length of the data in bytes, 0 to 8 bytes. Data contains the actual data values, which need to be scaled or converted to be readable and ready for analysis. CRC, the cyclic redundancy check, checks data integrity. ACK, the ACK slot indicates if the CRC process is okay. EOF marks the end of the CAN message. That's a lot, but only 3 are practically relevant in most data logging scenarios: the CAN ID, the control, and the data field. This is also why you typically only see these in CAN bus data output. CAN provides the basis for communication, but not a lot more. For example, the CAN standard does not specify how to handle messages larger than 8 bytes or how to decode the raw data. Therefore, a set of standardized protocols exists to further define how data is communicated between ECUs of a given network. Some of the most commonly encountered standards include SAE J1939, OBD2, and CAN Open. SA J1939. This is the standard in vehicle network for buses, trucks, and other heavy-duty vehicles. All J1939 messages rely on the extended 29-bit CAN identifier. Further, J1939 data parameters, an example RPM, vehicle speed, are identified by a suspect parameter number, SPN, which are in turn grouped in parameter group numbers, PGN, containing 1 plus SPNs. With this standardized structure, CAN messages from example buses and trucks can be scaled and decoded into readable data using parameter tables from the J1939 standard. Further, several standards are derived from J1939, including, an example, the Fleet Management System, FMS, which is freely available and included in Canvas. For more information, see our simple intro to J1939 or our J1939 ID to PGN converter. OBD2. Onboard Diagnostics, OBD, is a self-diagnostic and reporting capability that, an example, mechanics use to identify what is wrong with your car. The OBD2 standard specifies a number of standardized diagnostic trouble codes, DTCs, which can be retrieved by a CAN logger or diagnostics tool for any vehicle. But what makes OBD2 really interesting? OBD2 supports data on many basic real-time parameters, an example, vehicle speed, RPM, fuel consumption. This means that OBD2 is also used for an example, real-time vehicle telematics or post-analysis using CAN data loggers. Applications include vehicle fleet management, fuel optimization, proactive vehicle diagnostics, and more. To log OBD2 data, the CAN logger must request the data by submitting pre-specified CAN frames with specific parameter IDs, PID, to the CAN bus. When using the CAN logger X000, this can easily be configured in Canvas. For basics on OBD2, check out our simple intro to OBD2, or check our practical guides to logging OBD2 data or streaming it in Wireshark. CAN Open. CAN Open is used widely, an example, industrial automation applications. It builds on CAN in terms of physical layer, an example, lines used, voltages, and the data link layer, an example, utilizing a CAN frame message based on protocol. In practice, this means that a data logger, like the CAN logger X000, is able to log data from CAN Open applications, though the method of ex-post data conversion will vary depending on the specific application. Our Intel page contains several intro articles, uses cases, and guides. Let us know if you have more suggestions for the series. Interested in our products? Read more about our CAN Logger X000 series of CAN bus data loggers here.